Hello.
Hello, Sahil.
Hello, sir. So I just wanted to ask. So I had sent the homework to you earlier, but I think I had made a mistake in it. So,
1 second. Yeah, 1 second.
sure, sure.
Yeah, tell me.
Yeah, so I had sent you the homework
Yeah,
couple of days back, but I think I
yeah.
had made a small mistake in it.
Okay, let me um homework 2. Okay. Sigma S shall be S. Okay. So did you draw the monoid elements? So for
No, so I was actually trying to do it the way we did it in class by writing all the transitions and finding a presentation.
okay, yeah. A is equal to AB.
So the first problem was okay. That was just the three element, the B equal to 1, because B just keeps all the states at their own, since we are only looking at A.
Yes, yeah.
And A cube is again 1 because it comes back to the same state.
Yeah. So once you write B equal to 1, you don't have to write A equal to AB, A equal to BA, B equal to BB.
Right, exactly.
Yeah.
So
Okay, and B is equal to triple A, double A equal to A, B. Yeah. So that is all subsumed by B equal to 1.
yeah, exactly. So no, so the list which I had created, that
Yeah.
was actually computer generated. So the computer actually just blindly went through all of them.
Okay, okay. You wrote a program.
Huh.
Right.
And then later I've mentioned that if we just look at it and try to, I mean, once we have the list of, so the computer kind of keeps calculating till elements start, just keep repeating, no new elements occur.
Yeah.
And then we can just like go through the list and see which ones are the minimal ones.
Yeah.
But I think in the second one, I haven't mentioned all of the ones. I just saw the first few and I thought that I had the complete answer, but I think there's a little mistake there, I think.
A square equal to A, B square equal to B. Yes, B square equal to A, B square equal to B. There should be one more thing.
Yeah, because I later realized that this would, with these two conditions, the monoid would still be like infinite.
Yeah. So the ABA should be a 0.
Yeah, yeah, right. So I think I've mentioned that in a follow-up email. I've just written it in two conditions which say ABA equal to ABAB.
Yeah. AB.
And ABA is also equal to BABA. So basically, ABA multiplied by B, I mean, B multiplied by AB on either side, you'll get the same thing.
Yes, it will be 0. ABA.
It will be 0, yeah, as you said. So I forgot to write that in the assignment, but I mentioned it in a mail I sent later. So I'll make the corrections again.
Yeah. So once we go to the next chapter, you will be able to visualize these monoids much easier. Right now, they are still like a black box. Yeah. I mean, you
Right.
have
Yeah.
this equation, but we are not able to visualize them. But in the next class, I mean, next chapter, we will start visualizing these monoids.
Okay. Sure.
the Yeah, actually, I was of the impression that the class is for 1 hour, so that's why I used to stop the class after at 11:30. So now I know that it is not for 1 hour; it is for 1 hour 15 minutes. Why is okay? Is this recording? Yes, it is recording. All right, let's start. So last time, what did we do? Last class. So given a DFA, we learn how to construct the transition monoid. And actually, I forgot to tell you that we forgot to define what is accepting set and what is the morphism. So the morphism was quite simple. Delta map A maps to A in A maps to A in A maps to the transitions Q to Q dot or W. Let's say W. W in A star maps to Q dot W. Q to Q dot W. Yeah, this is what we called. This is what we call transition monoid, the set of such elements, the transformations on the states. And what is accepting set? If you are given L, what is accepting set? Somebody? Hello? For L, what is accepting set?
H of L.
Okay. Yeah, H of L, but can you be, uh, can we be explicit? Like, what are the elements here? So if your automata is QA dot Q0 and F, accepting set will be nothing but all those, let me call these elements as delta. Yeah. All those deltas is that delta of Q0 or Q0 dot um, mess of notation. Delta of Q0 W is in F. Yeah, all those transitions or extended transition which takes inertial state to a final state. Okay, so that's what your accepting set is. Okay, and then we learned how to compute this, and today let's do the same construction for let's do the same construction for NFA, and it will have some interesting applications. Okay, it will show some. Okay, so I have an automata that Q del A, and let me call it delta and I and F. Okay, delta is subset of Q cross A cross Q, and I F subset of Q. Okay, I have a non-deterministic finite automaton. Now I want to construct um, the transition monoid for this NFA. Now, what I'm going to do is this. Um, for I have a, let's imagine A is equal to AD for the moment. Okay, A is equal to AD. So now for each letter A, I can actually imagine a matrix of dimension Q cross Q, and the PQ element is labeled by 0 or 1, 0, 0 if PAQ is not in delta, 1, wait, 1 if PAQ is in delta, and 0 otherwise. Okay, I can construct these matrices. Now what I'm going to do is that, so now let me define this map H. H of W, H of A1, AN, I define it to be H of A1 times H of A2, etc. times H of AN. Okay, so I have a matrix for each letter A. I have a matrix which is nothing but a 0, 1 matrix. The entry at PQ is labeled by 1 if the transition PAQ is in delta. Otherwise, it is labeled by 0. And I define H of A1 to AN. I have a long word A1 to AN. What I do is that I just multiply these matrices. And what is my, so to define the multiplication of two matrices, I have to define what is addition and what is multiplication. And addition is nothing but, addition is Boolean or, and multiplication is Boolean and. Okay. Now, so let's try, if I have, let's imagine if I have uh, P0, P1, P0, P1, P1, P2. So let's go Q0, Q1, Q2, Q0, Q1, Q2. If I multiply two matrices, Q0, Q1, Q2, Q0, Q1, and let me call this matrix A. Let me call this matrix A, and let me call this matrix B. So if I multiply these two matrices, what will be, let's imagine this is going to be a matrix C. Okay, so this C, Q0, Qi, Qj. So if I, this matrix, let me just write it explicitly. What will be the first element? A Q0, Q0 times B Q0, Q0, the first element, okay, plus A Q0, Q1, B Q1, Q0, plus A Q0, Q2 times B Q2, Q0. Okay, this is the first element. So if I look at the ijth element, Can you tell me what will be the ijth element of C? Cij, Qi, Qj will be. Can you tell me what will be the ijth element? It will be A Qi Q0 times B Q0 Q Qj plus, and I can be little summarize. I can just write it over summation over all Qk. Yeah, this will be this product. So see, basically this element at Qi Qj is summation over all states Qk such that A Qi Qk times B Qi Qj. In other words, what it basically does is, uh, if I multiply two matrices A and B and I get a third matrix, the ijth element here is basically talking about the ijth element here is actually saying whether there is a path from Qi to Qj. And that is taken to be if there is a path in A from Qi to Qk, and if there is a path in B from Qk to Qj. Questions? Hello? Any question? So basically, we can show a small proposition which says that h of a1 to an, so this is a matrix. Let me call the ijth element the ijth element of h of a1 to an is 1 if and only if there is a path from Qi to Qj on the word a1 to an. A1 to n. Now, how do you prove such a proposition? You prove such a proposition by simple induction, by induction. Okay. Base case holds by definition, because for a simple letter h of a, you have defined this matrix in such a way that the entry is 1 if and only if there is a path. Okay. Now, for inductive case, you will assume for words of length n. Okay, and then for a word of length a1 to an, for a1 to an times an plus 1, you have assumed that this matrix on which a1 to an, the image of this word is actually a matrix in which one, if the entry at Qi Qj is 1 if and only if there is a path from Qi to Qj on a1 to a, and then this is actually multiplying that matrix by the transition which corresponds to the letter an plus 1. Okay, and when you multiply these two matrices, you will get that it will expand to a summation over this form. And here you just observe that this summation is 1 if and only if there is a path in A from Qi to Qk, and there is a path in Qj to Qk to Qj. And this just holds by the fact that you are defining plus as Boolean or and dot as Boolean. Is that clear? Yeah, that clear exercise. Complete the details. Yeah, is that okay? Anybody? Hello, Dhruv.
Yeah,
Yes,
this
sir,
seems
it's
okay.
fine. It's fine, sir.
All right. Okay, so that is what is a transition model, and this matrices. How many such matrices are there? If you have an automaton, some observations. If you are given an automaton Q A delta I F, what is the size of the number of matrices of dimension Q cross Q is finite because they are basically Boolean. They are basically Boolean matrices, and so therefore there can be only at most 2 power Q cross Q matrices. Okay, and from this observation you can do some examples. So let me give you one application of these, the way the the usefulness of this view. So you know that if L is regular, assume L is regular. Okay. Now this is a standard exercise problem. Half of L is equal to all U such that UW is in L and WU is of length W. Yeah. So half of L is all words of length U or all words of some length. All words U such that there is some UW in L and the size of U is equal to size of W. How do you do this problem? And you have to show that half of L is regular. How do you show this? Half of L is regular. Anybody remembers?
I think you can keep like two automatas, one with the starting state as the starting state, and another with the final state as the starting state. And
Mm-hmm.
then each time you move one step forward in the automata with the starting state as the starting state, you move one step backwards in the automata with the
All right.
state.
That's one standard idea. So many people also do it by pebbles. Yeah, you can imagine keeping two pebbles, one at the starting state, one as the uh, end state or some arbitrarily finished, arbitrarily guessed state, and then moving in synchrony these two pebbles one at a time, and you will finish when. So basically, uh, the idea which who was it? Who told me this?
Me, Argadeep.
Argadeep. So you can take two pebbles, one at the initial stage. So be let me just give a variant of this idea. So you start at you take two pebbles. One you keep it at the one in initial state. So it's an automatic finite automata. So you take two pebbles. One you keep at an initial state, and then one you keep at some arbitrarily guessed state Q. So this one I'm going to call Q0 and arbitrarily guessed state QF. And then each time what you do is that you move this pebble to one transition by one transition, you move this pebble by one transition, and when you finish you should end up the initial pebble should end up in the state q, and this pebble should end up in the final state, some final state. Okay, so this is one standard idea by which this problem is solved. But this the problem with this, I think you might have all seen this in your TOC course. Yeah, anybody who hasn't seen this? Okay, so you might have seen this idea in your TOC course, and but the one problem with this idea is that this is not very useful when it comes to solving problems like I'll give you some examples. So let's imagine L is regular. Now um, let me talk about uh, so this is half of L. What about L prime such that I'm going to write in the same way. U such that UW is in L, and so this general uh, a general version of this problem can be seen as U or length of W is equal to F of length of U. Yeah. So here it is nothing but F is nothing but equality. Yeah? So let me call this LF. Okay. So I have a language which is L, which is regular, and I'm interested in LF, which is all U such that UW is in L, and length of W is a function of length of U. And here you have taken from F to be equality for half of L. But you could also take F to be some arbitrary function. Like let's imagine F is the function 2 power n, or F is the function 2 power 2 power n, or F is the function Fibonacci. Yeah, Fibonacci, and so on. Now, what happens is that our typical intuition about regularity goes against these kind of functions. Yeah, we don't associate regularity with these kind of functions. I mean, most of the time, our regularity is sometimes some kind of periodic function. Yeah. Uh, so, how do we do this? So here, the transition monoid comes to our aid. Okay, so let me just explain how we can see half of L using our transition matrices. So um, I have the automata for L, which is Q A delta IF. Okay, and delta is the by delta I mean the matrix that corresponds to all the transitions. Okay, what does that mean? That means that delta of ij is equal to 1 if pi or qi a qj for some a n a. Okay, so you understand what is this matrix delta? It's just so there is an entry will be 1 if there is some transition, and otherwise 0. Otherwise 0. Okay, now let me construct a new uh, let me construct the semi group uh, let us construct all matrices generated by delta. Let me call it let me call this set by S. Okay, all matrices which are generated by, so in particular I, which is the identity matrix, which is equal to delta power 0. Okay, I'm assuming that delta power 0 is equal to I. Okay, so it's all the matrices generated by delta, So I'm going to call this set S. And I can construct what an automaton whose states are nothing but S cross S. Okay, whose states are nothing but S cross S. So basically, and what is the initial state? Initial state will be I comma I. What will be the next state? Next state will be on a letter A, it will go to delta comma delta. On another letter, it will go to delta square comma delta square, and so on. And on A1, on A2, and on AN, it will go to delta power n comma delta power n. What should be the final states? Are you following me? Anybody following me? Hello?
Yes.
Yeah, so what should be the final states so that I accept the words half of L? Anybody? You see how this states are, I mean, what, so in general, what is the transition relation? In general,
So,
as
uh,
yeah, in general, a state of this matrix, a state of this automata will be of the form m comma m, and on a letter A, it will go to m dot delta comma m dot delta. Okay, transitions. And what should be the final state?
maybe delta power 2k comma delta power k.
Uh-huh.
Like no, that won't work. Okay, never mind. I don't know.
Yeah, somebody else? Dhruv?
Basically, we multiply I to delta to the 2n times f, and if it's 1, then we accept it.
Yes. So final states, I will say all those m, because I mean, you see, every time it is going from, it is starting from the pair I, then I delta delta, then it's going to delta square, delta power n, etc. Okay. So I accept when I reach a pair such that there is a problem. I used initial state also to be, so let me call in and fin. Okay. In is for initial state, fin is for final states. Because I come confused between this. I is not the initial state, okay? Or the I might have confused you. I is actually the identity matrix. Okay, so I accept when in times m times fin is equal to 1.
So one thing I didn't understand, why are you taking S cross S?
It's
Because then
11
you can
o'clock.
just take S, right? Because like you are not using basically both the coordinates are giving you the same information. So
Yes,
why take
yeah.
two coordinates?
Yeah, so the point is that I just wrote it this way so that when we do the next, so in this case it happens that both these coordinates are keeping track. So basically this is exactly what the idea which I was doing here. Yeah, in this case I placed two pebbles and then I'm moving to the right in each of these components. Similarly here, what I'm doing, I for every letter I'm keeping two coordinates, and I'm moving my automata to the right in each of these coordinates, and I'll accept when the initial state composed with the first component and the second component, it reaches a final state. So if there is a path from initial state to some given by this first component and then given by the second component and then reaches some final state. Yeah, this is what.
Yeah, but I didn't understand why this equation will, whatever the final state you have given, will give you the required thing.
We're starting the coordinate from I comma I, right?
I comma I is nothing but delta power 0 times delta power 0. Okay.
So I is identity matrix,
Yeah,
right?
I is identity matrix.
Yeah, but I do not understand why this gives you the required thing.
Because
So
now let's imagine, if there is if you start from the identity matrix and reach m comma m, that means that you there is a any word. So let's imagine you start in I comma I and you reach m comma m, okay, on some word w. This means that there is a path from initial state on w to some m. Okay, so if you start from the initial state and you read the word w, then you will start reach this matrix, and here you can read some other word. Okay, so it may not be the same word, but some other word w prime, or even the same word will also work. You will reach a final state. Yeah.
Where is this MW prime to Fn happening? I'm not getting that.
Pardon.
I mean, both the coordinates starts with I comma I, right? And
Yes.
on W it's going to M comma M. So where are we? Where is this computation happening? From M to W prime to Fn?
This computation, so I create a new automata. Okay, so I have these matrices. I know that the such matrices are finite. Now I can define a new automata with the set of states to be s cross s, the initial state to be I comma I, and then the transition relation m comma m2 on letter A goes to m dot delta comma m dot delta, and final state to be all pairs mm such that in times m square times final state is equal to 1.
So here we are just keeping track of the length of the word, right?
We are just keeping track of the length of the word, but not just the length of the word. What are the states on that length? The automata can go from initial state to some state.
Right.
Yeah.
But as in, if say a word of length to as in length A is accepted,
Mhm.
then won't this give us that all the words of length A would be accepted, which is not necessarily true?
Pardon me. Yes, if a length of if a word of length k is accepted, then you not all words of length a can be accepted. No.
Right, but this is as in, if our construction is correct, then that is precisely what we are getting, right? Because nowhere we are keeping track of the word itself, as in what's being stored in delta power I is just the length of our word.
No, no. One second. Huh? Um, Ah, 1 second. I think yeah. All right. Okay. Ah, inter. Okay. I made a small mistake here. Okay. So the mistake I made was that. So delta. Okay, is a matrix that corresponds to all the transitions. Okay, delta is a matrix which corresponds to all the transitions. Similarly, I will call delta A to be the transition matrix on A. All right. Now here I made a small mistake. It's not a small mistake actually. It's a giant mistake. So here I'm not going from delta to delta. Instead, where am I going? I'm going on letter A1. I'm going to delta A1, comma delta. And on A2, I'm going to delta A1 times delta A2, comma delta square, and so on. Okay, so on on a on two matrices M and N, I go to M dot delta A and N dot delta. Okay, and then now if I have M and N and I go to M times N times Fn is equal to 1.
Okay, so small clarification in the notation. What is IN, FIN, and 1 in the equation?
In is the initial states. Initial
So,
state is a column vector. Initial
okay,
state is a row vector. Final state is a column vector.
okay, and 1 is the identity matrix.
One is just one, the number one.
Ah, okay, yeah, 1 is 1. Yes, yeah, 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 right, right.
Yeah. So
Is the monoidal one, right?
no, it's just the number one because anyway, this is just our boolean 0 and 1. So now, is this construction clear? I mean, I giantly screwed up, but I hope the construction is clear to everybody. Anybody? Any questions?
Do
So
you
what?
mind scrolling back up to the delta definitions once more?
Yeah. So I have an automaton Q A delta IN fin. IN uh, is a matrix like this, 0. Um, so QI 0, or let's say Q1, and this is 1 if Q0 is initial. If Q0 is initial. And fin is nothing, a column matrix where entry is, let's say, entry is 1 if Q0 is final. Okay, and so on for others. Okay, so the idea is that when you multiply, uh, whenever you have a matrix, you multiply by in to the left and fin fin to the right, it will give you one element because this is 1 cross q, this is q cross 1. So when you multiply 1 cross q times, uh, uh, sorry, when you multiply 1 cross q times q cross q times q cross 1, you will get 1 cross 1 matrix back. Yeah. So, so basically, the idea is that when you multiply column vector times a transition matrix times the final states matrix, you will get a number. If that number is zero, it means that there is no run from initial state to a final state. If that number is one, it means that there is a run from initial state to final state. Okay. So now, so I take this automaton. Delta denotes the matrix which corresponds to all transitions. Delta A denotes the transition matrix which corresponds to the letter A. Okay. Now, if I have my automaton, from that I can generate all matrices generated by, I have to be clear here also, generated by delta A, delta B, etc. Okay. So the entire transition matrix, the transition matrix which corresponds to individual letters and so on. So now I'm constructing a new automaton. That new automaton, what does it do? It keeps track of the transition matrices. Okay, so the new automaton, it is state is of the form S process. It starts from the identity matrix, and on letter A1, it goes to delta A1 and delta. On A2, it goes to delta A1 times delta A2 time, comma, delta square, and so on. So in general, a transition, if you have a state Mn, on letter A, it will go to M dot delta A, comma, N dot delta. So in the first component, I'm keeping track of what is the word I'm seeing. In the second component, I'm just keeping track of all the transitions which are possible on a word of that length. That's what this N dot delta means. The first component keeps track of what is the word which is seen on A1, A2, etc. The second component keeps track of what can be a possible transition, what all paths exist on a word of length, on a word of that length, which I
So
have.
n essentially stores the information of the size of w, basically how long w is. So basically
It
that
is,
says,
it is
yeah,
keeping track of all the
yeah,
possible paths on of,
of length, the, yeah, size of it.
yeah,
So basically then you read from in w to m, and then using n you say that okay, I'll just read something of length equal to w, and then we'll reach final.
exactly.
Yeah, yeah, this makes much more sense now. Yeah,
All right. Is this clear now?
yeah, 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 yeah.
So
Yes.
I had a question.
Yeah.
So suppose we have the language L, and so suppose we know that it is a regular language,
Yeah.
and that means that we have a homomorphism which recognizes that language, right?
Yeah. Yeah.
So is it possible to synthesize the homomorphism from this homomorphism that recognizes half of L, like
Uh, yes, it is
just
possible.
from the homomorph
Synthesizing means that,
algebraically?
meaning that if you want to find out this, you have to. I mean, it can, or it can be accepted by a matrix monoid or a semigroup. Any, yeah. So if you have if you have a set of matrices which accept your original language, then from that you can create a new set of matrices which will accept your new language.
So you mean to say we already always need to go through the automata approach to synthesize that semigroup monoid, is it?
It's not automata really. It is actually multiplying these matrices. You will see that you can, till this point, you could actually keep track of this intuition about pebbles. But in the next examples which we do, this intuition about pebbles don't really work anymore. Okay, let's do Fibonacci. Let's do Fibonacci. Okay. So basically, L is regular, and I want to find fib of L, which is all u such that uw is in L, and length of w is equal to the youth Fibonacci number. Okay. So Fibonacci number starts like 0, 1, 1, 2, 3, and so on. So this is let's call this to be the ith Fibonacci number. So this is first Fibonacci number, this is second Fibonacci number, and so on. Yeah. So how do we do Fibonacci? Can somebody tell me? Or maybe we just jumped into this pretty little fast. Let's do something which is naturally from follows from this. Um, let's do. We just did half, so let's do. Uh, um, f is equal to 2 power n. Okay, so basically what I want to do is that lf to be u such that uw is in L and the length of w is 2 power length of u. Okay, so now I claim that again my S cross S states automaton with states S cross S. What is S cross S? The one which we just described, the set of states, all the matrices which are generated from delta, delta A, delta B, etc. Okay, delta cross del and initial state to be I comma I, the identity matrix, and transitions. So here transitions matter. So if you have M and N on letter A, where should it go? It should go to M dot A, M dot delta A, comma, and where should N go?
N square.
N square. Okay, that's true. Let's understand why. So initially I start in I comma I. On letter A1, I go to delta A1, comma, delta. Yeah. So I have to start at so initially I should start, if I want to do that way, I have to start with delta. So it goes to delta square. And on A2, I go to delta A1, A2, and delta power 4. And next A3, I go to delta A1, A2, A3, comma, delta power 8, and so on. Is this clear? So initial state is not I comma I, it's I comma delta. Okay. And what are my final state? Final state is all pairs Mn says that I in times M times N times fin is equal to 1. I think this is the case with almost all. Yeah. Is this clear?
Yeah.
Yeah.
So now this time you don't have this analogy with the pebbles and things like that, or starting an automata. That kind of automata analogy does not work. It just how happens that the matrices we are generating are finite, and you can hardwire your transitions in such a way that they go to the desired metrics. That's why it works. Okay, and so yeah. And how do you do? So let me give you an exercise. F to be, take F to be 2 power n. Okay, 2 power. And let's me do this also. What's the time now? Okay, enough time. What about F to be F is equal to n square? This will need a slightly different idea, n square. So basically, I'm looking at a language L is equal LF is equal to all u such that length of u equal to length of w is equal to length of u square, comma u w is in L. So how would we do n square?
So do we keep track of a triple instead of a tuple, and one
Okay,
of the elements will be squared of the
yeah.
other?
So the states will be q s cross s cross s cross s, and you will initial state will be. So the idea is that if you look at delta power uh, n plus 1 square is equal to, so n plus 1 square is nothing but n plus 1 square is nothing but n square plus 2n plus 1. Okay, so that means that if I have to compute delta power n plus 1 square, this is nothing but delta n square plus I'm confused. I'm getting confused by my own notation.
No, you mean to say delta n squared times delta n times delta n.
Yeah, delta n square times delta power 2n times I. No, delta. Okay. And so basically, if I want to compute delta power n plus 1 square, so imagine if I am in a state, I have already delta n square. Okay. And when I go to the next state, I have to compute delta n plus 1 square. And if I want to compute this, I need delta 2n. And I also need, I just need these two elements. Okay. And then I can compute delta power 2n plus 2. So therefore, my states will be S cross S cross S. Initially, I'll start with identity matrix and then delta, comma, and this is um, delta square. And from here,
On reading a, I times
I,
delta a,
comma.
comma, so
So
can you write it as this I comma m comma n?
let me call it C, comma D.
Yeah. Okay.
Okay.
So
So this is
that will
which keeps track of n square. This is what is keeping track of 2n.
do it. Yeah.
No, so that shouldn't be I, right? I mean,
Right?
it should be some other matrix.
Something. Yeah.
So let's call it m, c, and d. And m dot delta a times c
Uh,
e times
plus.
delta,
Yeah.
comma d times delta, d times delta square.
Delta square.
Delta square.
Okay, because now this, if this is n square, this will become n square times 2n plus times 1. I mean, n square plus 2n plus 1. And you multiply these two matrices. And this will become n 2n times 2n plus 2. So that is 2 in n plus 1. Yeah. Yeah.
Yeah.
Okay. And initial state will be, so I think if you take it to be I comma what is C?
Identity.
No, I don't think identity will work, will it?
So the initial state will be the column vector that we have, or the row vector. Then the identity matrix, and then again the identity matrix.
I comma I is what you're saying?
No. So the first I is actually the initial vector I,
Yeah.
but the other two i's are the identity matrices. So you can differentiate them with some notation maybe.
No, our initial state is I, right?
No, initial state will be the row vector which tells
No,
you
no, no,
which
but
state.
that is
No.
the final state. For the final state, you will all final states, you will just multiply it explicitly. So if it is MCD such that I initial IN times M times C times FIN is equal to 1. So you don't have
So
to keep track of.
so third coordinate should not be I, right? It should be I. Sorry, it should be I square or something else. Like because
I
so
square is nothing but I.
oh wait I square or delta square. So because uh n square on one is 1, but 2n on 1 is 2. So we have to take care of this. We need this 2 information 2 already, right? For the next step, don't we?
Yes. So it has to be like I plus I. So
Uh,
2 times I.
yeah,
No, but there is not 2 times I. It's I plus 2 times I is
We're starting at n equals 0, right? So that
no,
takes
the
care of.
first one is not 0, right? Because you have path of length 1. The first like any matrix tells you there is a path of length 1 on this letter or any letter. So
yeah. But I plus I is nothing but I because it's a Boolean addition.
okay.
Okay. So I think that takes care of it.
So for like Fibonacci, we can do something similar, right? We can have a triplet.
Now I give you an exercise, Fibonacci as an exercise. Exercise. Do Fibonacci. Yeah. If take f to be f of n is equal to nth Fibonacci number. Okay. So yeah, so can you tell me the idea? So if you will keep track of two numbers, one will be the initial part m, the other will be the nth Fibonacci number. Let's call it f. Uh, uh, and fn minus 1.
Yeah,
And
so in the next step, basically we multiply it with m times delta A, then we multiply fn and fn minus 1 and then keep
fn,
f. So here it will be fn times fn minus 1.
fn minus 1, and here it will be fn. Yeah. Yeah. Hello.
Yeah.
Yeah, yeah.
So that will take care of Fibonacci. And okay. And so this way you can do many functions. You can do any polynomial. You can do many functions. In fact, this is from a paper called On Regularity Preserving Functions by Dexter Corson. Okay. And in fact, any function f that is ultimately periodic for any f that is ultimately periodic, LF is regular. If L is regular. Okay. So that was an application of these matrices. Viewing these that is an application of transition matrices of NFA. Okay. All right. And so now you know how to compute transition monoid of a NFA. And let me tell you that if you have NFA, yeah, so this is another observation. If you have an NFA, you can construct the transition monoid of the NFA. And then you can, from this transition monoid, you can get a DFA. Yeah. And this is, so this way, instead of subset construction, when you want to go from NFA to DFA, usually you do a subset construction. You could go by just constructing the transition monoid of the NFA, and then from the transition monoid of the NFA, you could come back to the DFA. And so this is in this way you can you can get the equivalence between NFA and DFA.
But aren't we doing sort of subset construction when we go to transition monoid?
Yeah, you are doing a subset construction. But
Yeah.
my point is here that, so when you do the subset construction, there is a blow up. So when you go from NFA to transition monoid, there could be a blow up of exponential size.
Yeah.
Yeah. So transition monoid is exponential of 2 power size of NFA. Yeah. So transition monoid can be, so when you go from an automata to transition monoid, it could be exponential phase. Okay. And all right. So therefore, so now we have given an NFA or DFA, you know, one monoid which will accept this language. Now we are going to do a construction which is irrespective of the automata. Syntactic monoid. Okay. So what is this monoid? The idea is that given a language L, given a language L, there is a canonical monoid. Canonical. Canonical means that uh, there is a one specific monoid. Canonical literally means according to the law, because yeah, canonical monoid recognizing. So I should be specific. Given a language L, there is a canonical monoid, monoid recognizing L, and this monoid has this property that has the property has the that has a specific property. We'll come to the property later, which is that it divides. There is a morphism from any monoid recognizing L to that monoid. So in a way, that is the smallest monoid. Just like you have minimal automata, you have a minimal monoid, which recognizes L. That is what is called the syntactic monoid. Okay. So now our this thing is how to compute the syntactic monoid. Our next objective is to compute this the smallest monoid recognizing L. Okay, so the way we go ahead, we will go is by saying that if I have an L, I can define tilde L as follows. I'm going to define a congruence based on this language L. I'll say X is tilde Ly, where if for all UV in A star, UXB is in L if and only if UYB is in L. Okay. So basically what I'm saying is that my congruence tilde L is defined in the following way. Two words are equivalent, X and Y are equivalent if for any context, any left-right context, U and V, U on the left, V on the right, if UXV is in L, if and only if UYV is in L. Okay. Now, let's try to prove that tilde L is a congruence. So, first step is to prove that tilde L is an equivalence. So, X is tilde L equivalent to X. Why? Because UXV is in L if and only if UXV is in L. So, X is tilde L equivalent to X. This is done. If X is tilde L equivalent to Y, then if and only if, then Y is tilde L equivalent to X. That's also clear. If X is tilde L equivalent to Y and Y is tilde L equivalent to Z, then X is tilde L equivalent to Z. Why? Because you take any two contexts U and V, such that UX V is in L if and only UIV is in L, and you take UIV is in L if and only UZV is in L. Therefore, UXV is in L if and only UZV is in L. So this is also done. So it's an equivalence relation. Okay, so now we have to show that tilde L is a congruence. Okay, so for this, what we have to do? We have to show that if X is tilde L equivalent to Y, then XA is tilde L equivalent to, or let's say, let's do it this way, and S is tilde L equivalent to tilde equivalent to t, or let's simple. X is tilde equivalent to y, then xa is tilde equivalent to ya. And you have to do reverse also. Ax is tilde equivalent to ay, but that argument is symmetric. So we just need to argue this one way. X is tilde equivalent to y, then xa is tilde equivalent to ya. So x is tilde equivalent to y implies that for all uv, v is in L if and only if uyv is in L. This is what it means. So therefore, so this implies that uxav, okay, I am considering a context like u and av, is in L if and only if uxa uyab is in L. Uyab is in L. This will imply that uxa v is in L if and only if uyab is in L. So this implies that uxa is tilde equivalent to ya. Is this clear?
Yeah.
Okay. Any questions? Hold on. So this way we show that tilde L is a congruence, and therefore tilde L is called the syntactic congruence. It's called the syntactic congruence of L. Okay. And so you quotient A star with tilde L. It's called the syntactic monoid. Syntactic monoid. It's an abstract object, but it can also be understood as the transition monoid of the minimal automata. That we will do that in the next class. Okay. Yeah. We have time. I think that's enough for today. I think. Any questions?
Yeah, not regarding this, but you said there will be a quiz next week, right?
Yes.
So when?
Let's have it on next Friday
During the class time.
during the class time.
Okay,
Yeah.
sure.
For Fibonacci, Saturday, Mal, okay. Yeah, and you will all be able to turn on your video. Yeah.
Yeah.
Okay.
I don't have a webcam. I mean, my laptop is in repair, and my computer does not have a webcam.
Okay. So, but you have a mobile.
Okay, so I'll use it on mobile then. Fine.
So how will you? What you can do is that you can write it onto a sheet of paper, take a photo, and send it to me, or upload it in Moodle. Is that possible to upload it in Moodle?
Yeah.
Yes, sir, it is.
Yeah, you upload it in Moodle, and then yeah. So yeah. So basically, so far we have covered the basics of semigroups, how to prove using things using the axioms of monoid and semigroup. Then what is the congruences, um, semi-group presentation, some examples, then how to compute syntax transition monoid. Then this class we learn how to compute syntactic monoid, and yeah. And after the quiz, we'll go to the uh, the details of how semi-groups look like. Okay then. Thank you.
Thank you. Bye.
Thank you, sir.
Thank you, sir.